Hey guys, Mr. L coming back at you with another video, and in this video we're going to talk about atoms. We're going to give you a brief discussion of the history of atoms, the experiments that led us to the structure of the atom, as well as we're going to talk about average masses and isotopes, including the mass spectrometer. So if you haven't subscribed yet, hit the like button, subscribe, share this with your favorite monkey, share this with your grandma twice removed, and let's get into this video. So the first thing we're going to talk about in this video is a brief history. The brief history of the atom started with this Greek idea from a guy named Democritus, and he postulated a long time ago that everything was composed of these small individual particles that we call atoms. And this is pretty amazing, seeing that he didn't have the tools to even see an atom at this time. The first person to come up with the idea of a uniform atomic theory of this was an English chemist named John Dalton. And John Dalton had four primary areas which unified his atomic theory. The first piece of his atomic theory is that all elements are composed of very small particles called atoms, which is very similar to Democritus' view. We could see that this also holds true even though this was done a very long time ago. The second part of John Dalton's atomic theory is that atoms of a given element are identical to all atoms of the same element. But this has been revised because we have since used mass spectrometers to find out that there are these things called isotopes, which are atoms with differing mass even though they're the same element and have the same number of protons. And we'll define isotope later in the video. So this has been revised, as well as there's these things called ions that exist, and ions are atoms that have gained or lost electrons, giving them an electrical charge. The third part of Dalton's atomic theory is that atoms of an element are not changed into atoms of another element by chemical reaction, and that they're not created or destroyed. But we've also revised this with the advent of nuclear fusion and nuclear fission, which is splitting the atom into smaller pieces or fusing atoms together to give higher order elements. The fourth and final piece of Dalton's atomic theory is that atoms of more than one element combine in relative numbers to make molecules or compounds. The latter two of these have shown that we've given two laws that are credited for Dalton's atomic theory: the law of conservation of mass and the law of conservation of matter, or the law of multiple proportions. So the first one we're going to talk about here is the law of conservation of mass, which states the total mass of all the reactants in a reaction should give you the total mass of all the products. Or another way to state this is mass or matter isn't created or destroyed, it's just converted when we have a chemical reaction. The next law that we're going to look at here is called the law of multiple proportions, and what this states is that if two elements combine, they combine in whole number ratios, and they can vary. So an example of this would be carbon and oxygen chemically bonding together, and they could give you carbon monoxide, a whole number 1:1 ratio, or carbon dioxide, a whole number 1:2 ratio. But all this means is that elements are going to combine in simple whole number ratios, even though you may have multiple compounds that arise from two different elements. So now let's talk about the experiments that led us to believe the structure of the atom. The first experiment was performed by a guy named J.J. Thomson in the year 1897. And what J.J. Thomson did is he performed what's called the cathode ray tube experiment. And the way this experiment worked is that he had this vacuum tube with a fluorescent screen stuck inside, hooked up to a voltage source. And he found that particles were emitted from the cathode end, or the negative end of the tube, and flew to the opposite side of the tube through the vacuum, and creating this beam of green light in his cathode ray tube. So this fluorescent beam he called cathode rays, and determined that they were negatively charged because they were coming from the cathode end. So these negative particles we later discovered were electrons. So essentially what J.J. Thomson discovered was the electron itself, as well as its mass to charge ratio. The next guy that came about 10 years later, his name was Robert Millikan, and Robert Millikan performed what was called the oil droplet experiment. he had this chamber with two electrically charged plates in it, and he had this X-ray viewing lens, and he would squeeze electrically charged droplets into this device, and he was able to manipulate the voltage on the plates, causing these droplets to remain steady in the viewing lens. And from that, he could calculate what the overall mass of an electron is, or the overall charge. So after these two experiments within this decade span, we arrived at this model called the plum pudding model, which was how we thought the atoms were oriented, or what they were composed of. This was based off of this British dessert, which was this pudding with some dried fruit or raisins in it. So we thought the atom was essentially this solid sphere with electrons embedded into the side of the sphere. So the next thing we're going to talk about that's important is the idea of radioactivity, which is this spontaneous emission of high energy particles from an atom. They randomly just get put out based on its instability of that specific atom. And the first person to talk about this or discover it was a guy named Henry Becquerel, and there's a radioactivity unit named after him. Some other scientists that are famous working with radioactive particles are Marie and Pierre Curie, the people who discover radium. They would frequently walk around with radioactive particles in their pockets, and subsequently they died of old age as well as cancer due to these radioactive particles. But the most important guy that we're going to talk about dealing with these radioactive particles was a guy named Ernest Rutherford, and he gave us more of a modern idea of how the atom is oriented and arranged. So his experiment is a two-part experiment. The first thing he did was he put a radio emitter in a lead box, and he had two electrically charged plates that he would shoot these particles straight through the plates. And he noticed that with his detection screen, which was also a fluorescent screen, he would get three signals. One that went straight through, unaffected by the electrically charged plate, where we discovered that these are called gamma rays, or uncharged particles. These are high energy photons. So they are not actual particles, it's an electromagnetic light particle. The other two signals that he got were above and below the uncharged signal, and these were the advent of alpha particles, which are attracted to the negatively charged plate because they're positively charged. An alpha particle is a helium-4 nuclei, which is two protons and two neutrons all stuck together in a clump. A beta emission are going to be the emissions that are attracted to the positive plate because they're negatively charged, and those are the same as the cathode rays. Those are just electrons. So the next thing he did was he found an emitter that would only emit alpha particles, and he decided to shoot this at gold foil. And this experiment's called the gold foil experiment. So he was shooting alpha particles, which are helium-4 nuclei, at the gold foil, and he observed two major outcomes. The first thing he observed were that most of the alpha particles strangely went straight through the gold foil, but it wasn't leaving a hole or anything, but his strongest signal was on the opposite side of the gold foil. What that led us to believe that the atom is mostly empty space, which is pretty crazy and amazing. I'm mostly empty space, the tabletop's mostly empty space, buildings mostly empty space. So an analogy that a lot of people like to mention is if you were to go out into a pro football stadium or any other sports stadium with a pen, the tip of the pen would be about the size of the nucleus, and the rest of the stadium would be the approximate size of the rest of the atom. So most of this stuff is empty space. The other outcome he saw were these strange, smaller signals spread out throughout the room. And this was indicative of the positively charged alpha particle ricocheting off of another positively packed particle or some region within the gold foil, which we later found was the nucleus. So the nucleus had to have been a positively charged nucleus to cause these ricochets and repulsions of the alpha particle throughout the room in these smaller subsequent signals. So now that we have an understanding of these three different experiments, we can now have a better idea of how the atom is actually arranged. It's not that they're these solid indivisible spheres like Dalton and Democritus believed, but it's actually this small dense nucleus with protons and neutrons are what Chadwick discovered. We're not going to go over Chadwick's experiment, but neutrons are there in the nucleus to help stabilize the nucleus. So Rutherford discovered that there were these positively charged nucleus with an electron cloud orbiting the outside. And in later videos, we're going to talk about the electron cloud in more depth. So let's talk about the three important major subatomic particles. We've got the proton. The proton has an essential mass value of what we call 1. It's a relative mass value. We have neutrons with a relative mass value of 1. And we have electrons with a relative mass value of essentially 0. Electrons do have mass, but it's about a 2,000th of a proton or a neutron. So even in our biggest element that we have, which some periodic tables go all the way up to 112 or even beyond that, even if we had 112 electrons, that wouldn't even come close to the mass of one proton or neutron. So we say the relative mass is essentially 0. So let's talk about the charges of these three particles. Neutrons are neutral, so they have a 0 charge or uncharged. Protons are positively charged, so we say for every proton we have a +1 charge. And electrons are negatively charged, so for every electron that we have in the atom, we say that this is a -1 charge. So let's talk about how we even see atomic masses to begin with. We use a machine called a mass spectrometer. And the way a mass spectrometer works is there's a couple different important areas. The first area is the entrance or the sample portal area, and this is where you're going to put your sample. The sample is typically going to be vaporized at high temperature under acidic or basic conditions to cause an electron to be added or stripped off so that it can ionize. We have to have charged particles to go through the mass spectrometer. Then what's going to happen is the sample is going to go through this vacuum space where there's going to be some electrically charged plates or poles called quadrupoles. And what these are going to do are bend the flight path of the electrically charged particle through this vacuum space so that it can eventually hit the detector. Right before the detector, you're going to have what's called a mass filter, and the mass filter is only going to allow very specific mass to charge ratios to hit the detector. All the ones that aren't meeting this mass filter's guidelines are going to probably hit the sides of the instrument and are not going to hit the detector. So what the machine would do is it would go from low mass to charge ratio to high mass to charge ratio, and the computer would just move through those different mass to charges, and you would get these peaks and an output called the mass spectrum. And the mass spectrum is going to tell you all of the relative mass to charge ratios that sample you input had. So if we're talking about pure elements, if we're talking about something like chlorine, there's two major isotopes of chlorine. So if we told the computer to go from low to high masses, we would get two major peaks. We would get a chlorine 35 peak, and we'd get a chlorine 37 peak. So what we could see here is that chlorine has two different types of nuclei, one with mass 35 and one with mass 37, even though they're both chlorine. What they're differing here is with the number of neutrons, and we would never have been able to figure this out if we hadn't had this machine called a mass spectrometer. So all of the atomic weights that are on a periodic table, we typically see, unless they're those very rare radioactive ones, that there is a digit past a decimal value. It's not that these have a fraction of a decimal value, it's that when we go to calculate the average atomic mass, we take the percent abundance of each of these different isotopes and average them together, and it could be 70-30%, 50-50%, there might be 3 or 4 different isotopes. All you need to do is take the average atomic mass times its percent of abundance for one isotope plus its average atomic mass times its percent of abundance of the next, and do that for all isotopes, and you'll arrive at your average atomic mass total that's on the bottom of each of those little squares on the periodic table. So the last thing we're going to discuss in this video are the idea of atomic symbols. So these symbols are found on the periodic table, and they're either 1 or 2 letter designations that tell us something about the element. The sources of these names of elements or the symbols come from Latin sources, Greek sources, scientists who discovered them, or maybe some famous scientists, or the area where these elements have been discovered. The way that we show these symbols in its isotopic form is we typically write the total mass value, including protons and neutrons total, at the top of the symbol. At the bottom of the symbol, we typically put the number of protons, and the reason why we organize it this way is so that we can easily subtract and find the total number of neutrons, and that makes our math very easy. The top right of the symbol is reserved for charges. So if something like an ion exists, a +1, +2, -3, -2 charge, we're going to put those in the top right area of this symbol. So as we already mentioned in this video, we have the idea of what's called an isotope. An isotope is just an element that has a differing mass between two different atoms. So if we have something like carbon, carbon has many different isotopes. We have carbon 11, carbon 12, carbon 13, carbon 14. All of these carbon have 6 protons in the nucleus, or else this atom would not be a carbon atom. The reason why they're different 11, 12, 13, and 14 is they have different mass values, which is due to the number of neutrons in the nucleus. The two primary ones that you may have heard of is carbon 12, which is the most stable carbon, which is mostly going to be within us or other organic materials. It's going to be the most abundant source of carbon on Earth, as well as we have carbon 14, which is a slowly decaying radioactive form of carbon. And we use this for radioactive dating. So you could see that the difference in mass is going to give us different isotopes. So there it is, you guys. There's the video of atomic history and structure. If you enjoyed this video, if you found it useful, send it to your second cousin removed, send it to your favorite chinchilla, and we'll see you in the next video.